Today, the topic of discussion is on basic concept of strength of material, that is Module 1, Part 4, PCME 403. Myself, Dr. Suman Das, HOD, Department of Mechanical Engineering, Swami Vivekananda Institute of Science and Technology. Now, in this chapter, we will discuss the elastic constants and their relations, volumetric, linear, and shear strain, and related problems. Now, Hooke's law. So according to the Hooke's law, the stress is directly proportional to strain, that is normal stress, that is sigma, but proportional to normal strain, that is epsilon, and shear stress, that is tau, that is directly proportional to shear strain, that is gamma. So sigma equals to E epsilon. E is the modulus of elasticity, and that is tau equals to G gamma. So here G equals to shear modulus. So here the modulus of elasticity and the shear modulus, that is E and G respectively. Now volumetric strain, that is epsilon suffix V. So a relationship similar to the length change holds for the three-dimensional volume change. For volumetric strain, that is epsilon V, that is nothing but V minus V naught divided by V naught. So that is the change in volume by original volume. So we can write epsilon V equals to del V by V, that is P by K. Here V is the final volume, V naught is the original volume, that is del V is the volume change. So the volumetric strain is the ratio of the values with the same unit, so it is the dimensionless quantity. So del V by V, that is volumetric strain, so we can write epsilon x plus epsilon y plus epsilon z, that is epsilon 1 plus epsilon 2 plus epsilon 3. Now, Young modulus, we know that E equals to PL by AE formula. So, PL by A delta. So, that is P by A, that is sigma, and L by del by L, that is epsilon. Now, the modulus of rigidity of shear modulus, that is tau by gamma. So, PL by A delta. So, bulk modulus, that is K equals to minus del P by del V by P. Now, relationship between elastic constant E, G, K and mu. So, E equals to, that is we can easily establish the relationship, that is E equals to 2G 1 plus mu and 3K 1 minus 2 mu equals to 9 kg divided by 3K plus 6, where we know that K equals to bulk modulus, N equals to Poisson's ratio, E equals to Young modulus, and G is the modulus of rigidity. Now, for the linear, elastic, isotropic, and homogeneous material, that is the number of elastic constant required to relate stress and strain is 2. That is, any 2 of the 4 must be known. If the material is non-isotropic, that is anisotropic, then the elastic moduli will vary with additional stresses appearing, since there is a couple between shear stress and normal stresses for an anisotropic material. So here this is a problem. So in this problem, the modulus of elasticity and rigidity of a material are 200 GPa, 80 GPa respectively. Find all other elastic constants. So with the help of this formula, so we know that E equals to 2G 1 plus mu, and that is equals to 3K 1 minus 2 mu equals to 9 kg divided by 3K plus G. So with the help of this formula, you can easily calculate the value of K and the that is Poisson's ratio mu. Now Poisson's ratio. All of you know that the Poisson's ratio, that is the symbol mu, is nothing but the transverse strain or lateral strain divided by longitudinal strain. So this is the diagram. So if you see the diagram, if we pull the material in the along its axis, so it's the lateral dimension, so the length will be increased and the lateral dimension will be decreased. So this is the Poisson's ratio, that is lateral strain by longitudinal strain. So the theory of isotopic elasticity allows Poisson's ratio in the range of -1 to half. Poisson's ratio is a varying material. So this is the chart. From this chart, we can easily give a idea, give an idea that steel, CI and concrete, still the Poisson's ratio range is 0.25 to 0.33, and the rubber, that is the Poisson's ratio 0.8, 0.48 to zero point 0.5, and cast iron, this is the range, and cork nearly 0, and concrete 0.2, novel foam, that is negative. So this is the chart. So from this chart we can give you a broad idea about the range of the Poisson's ratio. Now the elongation of a body due to its self weight. So this is the elongation of the body. So self weight. So that value should be del equals to WL by 2AE, where L is the length of the member and W is the self weight, its own weight. The deformation of a bar under its own weight as compared to the when subjected to direct axial load to its own weight will be half. Now, the total extension produced in the rod of length L due to its own weight x per width length, that is del equals to, this is the value. Similarly, elongation of a conical bar due to its self weight, that is del equals to rho GL square by 6E. So the value should be WL by 2A max E. A factor of safety or safety factor. In the case of ductile material, there are two types of material in general. There is ductile material and brittle material. So in the case of ductile material, the factor of safety equals to the yield point stress by working stress. And in the case of factor of safety of brittle material, that should be the ultimate tensile stress by working stress. That is the sigma ultimate by sigma working. Now what is creep? Creep is nothing but when a member is subjected to a constant load over a long period of time. It undergoes a slow permanent deformation, and this is termed as creep. This is depend on the temperature. Usually elevated temperature, the creep is high. That means slow but progressive deformation with respect to time, that is called creep. So this is the diagram of tension test. You see there is a material. So this initial material, that is the L, that is L equals to the before the testing, and so this is the load is applied. Due to the application of load, the material is subjected to take load, and this material is elongated. So up to a point, the stress is directly proportional to strain, and this is the yield strength. So beyond that, there is the curve and ultimate tensile strength. This is the point, ultimate tensile strength, and this is the point, that is the fracture point. So this zone is called the elastic zone, and this is called the plastic zone. So within the elastic zone, the material can regain in its original shape, original position, but when it is goes beyond the elastic zone, that means entering into the plastic zone, material cannot regain its original position or original shape. And this is the neck formation. If you see the line, that is the green point, that is the necking formation. So the necking formation should be like this, and this is the fracture. So at the final point, that is the fracture should be like this. So this is the Testen curve of general ductile material, and this is also called, and material is the mild steel. Okay. So this, thank you very much.